Here we go. Good afternoon, everyone. My name is Julie Blomquist, and I'm the moderator for today's Database Professional Virtual Meetup group. Here's the information on our LinkedIn and our meetup, and here's the code image so that if you want to join or keep up to date with us. Please spread the word about our new platform. We're trying to get our attendee numbers and our membership numbers up. Our meetings are the second Wednesday at noon Eastern Time and the fourth Wednesday at noon Pacific Time. And the recordings will be available at the tiny URL here, or you could take an image. And we are recording the meeting today. And here's the location for the slide and demos code. We have future sessions coming. Here's who we have scheduled, and we're getting a full calendar. So please mark us down and join us when you're available. If you want to speak to our group, send us an email at the DBA-VUG@outlook.com. Here are some future events. These are Data Saturdays and SQL Saturday and SQL Bits. SQL Saturday and Data Saturday are one-day mini conferences. Some are in person and some are still virtual. So check them out. Today, I wanted to thank Bob Pusateri. Forget it, Bob.
No worries.
The ins and outs of SQL Server data compression. I really appreciate him taking the time to speak with us. And I'm going to stop sharing.
All right, I'm going to start sharing here. Hopefully that works, and I'll turn my camera on so you can see my ugly mug if you want. Hopefully everyone can hear me and see me.
Yes, I see the
all right.
presentation. Thank you.
Excellent, awesome. All right, so thanks everyone for showing up today. Thanks for coming. Hopefully we all learned something here today. Maybe myself even included. I hope. This is the ins and outs of SQL Server data compression. Just as a very brief introduction about myself. So I'm Bob Pusateri. I do a bunch of stuff with SQL Server and the Microsoft Data Platform. I help run the event formerly known as SQL Saturday in Chicago. Maybe someday we'll get to do one again, hopefully. But the most important thing you'll find on this slide is my contact information. So if you have any questions that we can't address during this session or at the end, or if you're watching a video of this later and something comes to your mind you want to ask me, please feel free to reach out. You can catch me on Twitter. My email's on here as well. And I will also have this information on the last slide. So you'll see it again at the end. Similarly, as was earlier mentioned, not only is this presentation being recorded, I also have all of the demonstration materials and the slide deck available for download. And I will put the link up to that at the end of this as well. So we're going to cover a bunch of different types of compression today, just compression in SQL Server and Azure SQL Database in general. We're going to start with a little bit of a primer, some basic things you should know about compression, no matter what type of compression we're talking about. We'll do a little bit of that, and then we'll talk about SQL Server row and page compression, which have been, pretty significant add-ins for SQL Server, being first introduced in SQL Server 2008. They're not new, they're not sexy, but they're very important. So we're going to see exactly how they work. And then we'll talk also about column store compression, which is in fact newer and can give us some extra advantages in certain situations. And then we'll take some questions at the end. If any questions come up during this session, I'll try to ask at a couple different points if we have any, so I can address them in a more timely manner. So why are we compressing data, right? And probably one of the biggest arguments you'll find against compressing data is this, right? Disks are kind of cheap these days, even though every once in a while they spike in price anyway, right? Flooding in Thailand or wherever in Asia they make disk parts always seems to make the prices fluctuate a little bit. But in general, you can buy a pretty freaking big hard drive these days for not a whole lot of money, right? You can get 12 terabytes. even larger than that. There's a whole community on Reddit called data hoarders, where it's people who literally just buy hard drives and accumulate tons of data for their own personal use. And then you buy external drives like pictured here, and you do what's called shucking, where you actually take the disk out of there and put some jumpers on it. You can actually just use it, usually for cheaper. But regardless, no matter how cheap disk space is getting, when you work in the professional data business world, you come to realize that the actual enterprise drives that most businesses should be using still are not cheap, right? You're paying for extreme levels of performance, you're paying for redundancy, you're paying for features like compression and deduplication that are built into the array. You're paying for support, right? If this thing breaks or if you need a drive swapped out, a lot of times these units will in fact contact support, and they'll just come out and swap the drive and nobody will be the wiser, things like that. So that's why, as cheap as disks are at your local big box technology store, in the real world of computing, not as much, right? So disk space, cheap, but not really. Still is a formidable cost. Same thing with maintenance, right? If we're talking about database maintenance in particular, right? Programs like DBCC, CheckDB and whatnot, they still have to read every page of the database, right? So if we're using database level compression, we can have the same amount of data on fewer pages. We can actually cut down on the amount of maintenance that is necessary, or the amount of time that maintenance might take, because there's actually less data to read because the data is compressed. Another thing to think about is memory, right? And this is a picture of actual hand-woven ferrite core memory. This is like 2 inches by 3 inches, and according to where I got this image from, it says it's 18 bytes. So there you go, ancient memory here. Memory is, of course, getting cheaper as well, but it's still more expensive than disk even today, right? And of course, memory is going to give you great bang for your buck, especially if we're talking in a database server. But if the data is compressed and we can store more data in the same amount of memory, well, now we can have better performance from the idea that we don't have to read from disk as much. So that can help us too. And then finally, I/O bottlenecks, right? So along the same lines of the last slide, right? If we can read from disk less, and disk is usually the most time expensive part of accessing data, well, then we can have better performance in general, and we can store more data on that disk. So that's all great. So to segue from this into, this is kind of why we compress. Let's talk a little bit about how we compress, right? Compression of data has kind of become part of our daily lives, whether we realize it or not, right? Images, audio, streaming video, these all use various types of compression formats. Even back in the days when Winamp was the only program on Windows that would play an MP3 file, because Windows Media Player couldn't really do much of anything yet. These are all examples of lossy compression. So we're compressing the data, which is great. We're saving space, but we're actually giving up some of the quality in return, right? Now, it's not a whole lot of quality generally, unless you compress it really poorly, and then you get all kinds of like artifacts, background noise in your music, or the images start looking horrible, like those memes you'll see on social media where someone's obviously doctored them like 20 times, and there's gigantic chunks of pixels hanging out in places they shouldn't be because they're poorly done. Lossy compression can give us great results or can give us terrible results, but you get to choose, right? That's part. And if you ever hear me talk about especially video compression, I love talking video compression. You get lots and lots of dials you can adjust on how much quality you want to lose, and have that video still look good or maybe not. Regardless, with lossy compression, right, the result is smaller of some amount of quality lower, and these are lots of formats, like I said, pardon me, JPEGs, MP3 files, H.264, H.265 video, H.266, etc. So that's lossy compression. We also have lossless compression, right? And when we're talking about the data world, this is what we want, because we don't want to lose any data just because we compressed it, right? If I compress a database and tell you, well, now some of that data is not there anymore, but you won't notice, well, that's not a real great argument, is it? So lossless compression is for instances where the data cannot change. A zip file would be lossless compression, or 7-zip, or any file compression utility you want to use. Those are all lossless compressions. You get back the exact same data you put in. Some people realize it, others don't, but all of the Microsoft Office formats, the newer XML-based formats that were introduced in Office 2007 and later, those are all zip files, right? If you have a docx or a pptx or an xlsx file from PowerPoint or Excel or whatnot, take and change that file extension to zip, and you'll be able to open it just like a zip file, and you'll see all kinds of folders and XML goodness inside there. So these are all examples of lossless compression where the data cannot change. Right, and there's lots of different types of lossless compression as well. Hofmann Coding is a great, albeit academic, example of lossless compression. This is where we try to analyze our data a little bit, determine what part of the data is repeated the most frequently, and then encode that with the fewest number of bytes. So maybe you have a huge amount of text and you have determined that the word "the" is the most commonly used word in that text. Maybe we would encode the word "the" with something very short, like a 1 or 2 byte sequence, whereas a word that isn't used very frequently at all will get a longer sequence, but overall we'd achieve great compression because we're taking the most frequently repeated part and making it very small. There's other examples of compression. A lot of them use some form of statistical modeling. I mentioned here on the slides, right? LZ77, 78, the gzip family, which is kind of built off of that. A lot of these all work the same way, which is they'll create some kind of dictionary of the most commonly used patterns, and then they'll reference that with a pointer, which is much smaller, and save a whole bunch of space. Okay, hopefully that's all making sense. Are there any questions so far? I don't see any. I don't have access to a chat room or something, but I'm trusting if someone has questions, someone can maybe butt in and interrupt me, or we'll just save it for the end. So we've talked a little bit about compression in general and why when we're talking about data, we probably want lossless compression, and there's lots of ways to achieve that. Let's talk about how SQL Server does that, right? Because access patterns in SQL Server, well, a zip file or a 7-zip file or any of these file type compression algorithms, you can get some great compression off of them depending on your data and how repetitive it is. So why don't we just take and zip the entire MDF database file, right? Well, that really wouldn't really work very well. And the reason is because this is great for big amounts of data, but it's not really good for small amounts of data. And SQL Server works primarily on small amounts of data, right? Even if we have a giant multi-terabyte database, all the I/O that SQL Server is performing is in terms of 64 kilobyte extents, right? So when we're thinking about that, database I/O is not only very small, it's very random, right? We're reading all over this file as we're scanning through. Sometimes it's sequential, then we get lucky, but we can't expect that. Again, all the I/O is actually taking place in terms of an extent in SQL Server, so 64 kilobyte chunks, and then we might be operating on an individual page beyond that. So this idea of compressing the entire file wouldn't really work very well. We'd have to decompress the file every time we did something, which would be all the time. That would be absolutely awful. And the name of the game with SQL Server data compression is you really need to balance the compression ratio and the speed, because even if I get great compression and save a ton of space, if it kills the performance of the database, then why bother, right? Nobody's going to want to use it anyway. So they really needed to find the sweet spot here between getting some good compression and, not making it very cheap in terms of fast to access. So where the data compression occurs in SQL Server is also quite important. And I'm going to have a very generalized, simplified model of the database here, right? We have users at the end who are querying, and when they write a query, when they write select star from table, blah, 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 that actually goes into the database engine and, of course, gets mapped to locations in memory, right? So there's what are called the access methods, which manage the access of the data. This gets mapped to pages on memory, or pages that should be in memory. If they're not in memory, then the SQL Server has to go to disk and retrieve them and bring them back into memory and operate them there. So when you enable database compression, and this, I mean row or page level compression on a table, which is really on an index, which is really on a partition, that actually takes place in the access methods. So what that means is the data is compressed when it is on disk, and it's also compressed when it's in memory. This is really good in terms of saving you space in disk and saving you memory space. As I mentioned, you can store more data in memory because it's compressed which means you'll have to read from disk even less frequently, and you'll save disk space as well. Those are the pros, but there's no free lunch in SQL Server or in anywhere else in computing, really. So the problem here, which isn't really even a problem anymore, but you will use more CPU slightly because that data is never cached anywhere in an uncompressed state. So every time you read this data from memory, you have to decompress it. So if you say select star from a table 500 times, guess what? You're decompressing that table 500 times. Something to keep in mind. Also keep in mind that, as I said, compression was released originally in SQL Server 2008, and it had a minimal performance impact back then. And I really hope for your sake that if you're, working on a machine today, that it's from some newer time than 2008. If not, it might be a great time to look for a new job. I hear they're paying tons right now for qualified engineers. So let's talk about the compression types in SQL Server. There's actually three different types now available. Originally there was two, then columnstore came along and it's a third. And this is by far the most impressive set of animations I've ever done in PowerPoint. We have row compression, we have page compression, and we have column store compression. There we go. So we're going to go dig a little deeper into each of these. I have some demos we're going to do. Hopefully they behave today. They were working earlier, and we will show you exactly what I'm talking about. And if there's any other questions, this is a great time to ask them before we get started with row compression here. All right, I'm gonna guess I've blown everyone's mind and we don't have any questions yet, which is fine. So let's talk a little bit more about row compression.
Wait,
we got one?
Will SQL Server backups be further compressed after performing the data compression inside the database?
That is an excellent question. The answer is yes. We do not cover backup compression in this talk because that is different. But when you take a backup, the backup process is literally just reading the pages off of disk, right? So whether those pages on disk happen to be compressed or not, it will read them in, it will try to compress them further. If those pages on disk happen to also be encrypted because you're using TDE, you can try to compress them, but the compression is not going to do anything for you because it's really hard to compress, effectively random encrypted data. But yes, if you use row compression or page compression or column store, and then you issue a backup with compression beyond that, there will be additional benefits. Any other questions? Okay. In fact, I think I have a slide on that later, but it might not be.
Yeah, one sec.
I forget.
Hey,
sure.
Bob,
yes.
Paresha, there's somebody else who's asking if we also have a compress function. We have also got a compress function. I think it's a statement more than a question. So
there is a compress function, and I believe the one you're talking about is where you can compress data in like an individual field, which is again something different. I'm just talking about the native engine features. You can totally roll your own kind of compression, and I've seen applications that have functions that are called something along compression, and some of them actually do compress, and some of them really just encode in like base 64 or whatever. But same idea. But what we're talking about here is just the native built-in features. All right, so let's go with row compression here. Row compression is, if you're going to be a purist, you might not even call it compression, because what it's really doing is it's helping you only use the space you need, right? So it's very lightweight. I would say cheap, but I feel like that's kind of an insult. Row compression will save you from poor data typing. It's more of an optimization than a true compression, but that's okay because poor data typing is something that a lot of databases deal with on a regular basis. So this is where row compression can possibly help you. First thing row compression does is any fixed length numeric data will become variable length. So if you're using a column, that's an int, right? Int is a fixed length type. The fixed length is 4 bytes. Let's say you're storing the value 5 in an int column, right, as I have on the slide here. Well, 5, you don't need 4 bytes to encode the number 5. You only need 1 byte to encode the number 5. You actually need less than 1 byte to encode the number 5, but the smallest it will go is 1 byte. So what row compression will do for you is say, hey, instead of actually using 4 bytes, we're just going to store this value in 1 byte. And there you go. You just saved 75% of the space. If you have fixed length character data, it will also become variable length, right? So the old, if you create a column and you call it char 100, and yes, I say char instead of car. I know there's various religious wars that happen on this topic. But if you have a char 100 and you're only storing something with 3 bytes in it, without compression, it would actually take up 100 bytes on disk, 97 of which would be empty. In this case, if you're using row compression, it will actually only use the 3 bytes that are necessary. If you have null or 0 values in numeric type columns, they'll take up no space at all, which is pretty cool. And then if you have variable length metadata, your overhead is reduced, right? So there is an actual different record structure. So for example, if you have a column that is varchar 100, right? So variable length character up to 100. Behind the scenes, whether you realize it or not, there's actually 2 extra bytes that are appended to that 100 byte column. And those 2 bytes are used to store the length of what's in that column, right? So if you have a varchar 100 and you have 5 characters stored in it, it will actually take up 7 bytes on disk. It'll take up 2 bytes to store the number 5, so you know that there's only 5. The length of this column is only 5, and then the 5 bytes of the actual data that are going on. But there's a new record structure, so if you're using row compression, instead of 2 bytes per column, it will actually only take up 4 bits per column for variable length columns of less than 8 bytes. These are called column descriptors, and we'll actually look at them in the demo shortly. But so the metadata can be reduced as well. As an aside from this, as a database purist, I'll consider myself, I find it mildly infuriating when you come across people who create a column of type like varchar1, because again, you have these 2 bytes behind the scenes nobody realizes. So you're actually using 3 bytes to store a 1 byte value where you could have used a char1 and not had those 2 extra bytes and just used 1 byte to store it. So something to think about there as well. Going on with row compression here. Row compression does not do anything with the smallest data types. So if you have like a tiny int or a small date time or a date or a time type, those don't get touched. If you use bit columns, hopefully you do if you have a need for them. The way bit columns work is when you create a column of type bit, it actually allocates a full byte on disk for that. And then if you allocate any more or create any more bit columns, it would use that same byte. So your minimum is a byte there, but with row compression, it's shrunk to actually half that. So it's 4 bits now. If you're using Unicode character data, right, your nchar or your nvarchar, you may get compression out of that as well. It uses what's called the SCSU algorithm, which is the standard compression scheme for Unicode. If there is an advantage to compressing the data, it will take advantage of it and use that. And if you're using nvarchar max, you don't get any compression at all. So this is great to talk about, but let's actually see it. Let's try to understand it a little better. So I have an example table here, and I have 2 columns in my table, right? I have an ID column, which is a small int, and I have a first name column, which I'm using as a char8 in this example. So without compression, small int, right, a fixed width type takes up 2 bytes. So we're taking up 2 bytes, and of course the char8 is always going to take up 8 bytes. So this is exactly on screen how it would look on disk if we were not using compression at all.
We're still seeing the row compression slide. Is that where you wanted to be?
You're seeing the one with the graphical picture of the
can crusher?
Really? It froze the image, huh? Okay, hang on one second. Let me.
No, I saw the other one. Now I see the can crusher.
Now we're back on this one.
I'm on the grid.
Okay, so this is affecting not all of you then. Maybe.
I don't know who was speaking. Do you see the grid now?
No, I'm still seeing the can crusher slide. Let me.
Interesting.
Try something here. Could be on my side too. So.
Okay. Well, I see the grid.
Go ahead and keep going. I'll watch the replay later.
Okay,
well.
That's fine. No worries. I say maybe rejoin the meeting. That might help too. I don't know. Okay, so we have this now. If we actually apply row compression, this is what's going to happen. It's going to actually slide everything down because, as I said, these fixed width types become variable width now. So for the first ID value for Sam there, ID was 92, right? You can store 92 in a single byte. You can store up to 255 in a single byte. So instead of taking up 2 bytes, that takes up 1. And of course, the name Sam only takes up 3 bytes instead of 8. So we just saved a total of 6 bytes on that particular row. For the second row, 43, 46, right? That requires 2 bytes, so that won't change, but we'll save some space in the name. The third row, we won't save any space in the name at all because Michelle is 8 characters, but her ID of 120 will save us a byte. So the amount of space you save with row compression is variable depending on what you're storing in there, but you're saving the unused space that you wouldn't need. Because nothing is fixed with anymore, just to point out, the relative shortcomings, which I don't even consider shortcomings. But remember, if you look at the top value, right, because everything's fixed with, when you're scanning the row, SQL Server can say, hey, you know what? They just selected the first name column. So I can just skip the first 2 bytes and start reading on byte number 3, and that's the first name. When you start applying compression and everything becomes variable with, you can't do that anymore. You need to read those column descriptors to actually figure out where every column begins. It's more work, right? It's a trivial amount of work that isn't going to cost you anything practical, but it's just something to think of, like, hey, there's an extra step involved here now. So with that, we're actually going to move on to the first of the demos here. And again, I have all this demo data and the notebooks available for download, so you can try these all yourself. I have here, and hopefully everyone can see this, I just dragged Azure Data Studio up onto the screen. Pardon me while I cough there. So we have here a database full of Chicago parking tickets. And I've blogged about this database before because I like to use it for fun demo data. So I have a couple million parking tickets written by the city of Chicago from 2003 to 2016, just to very briefly show you what I'm working with here. We'll go ahead and we'll run this first column, just select the first 100 rows. You can see we have lots of information, parking ticket numbers, license plate, where the plate was from, where the ticket was issued, what it was for, et cetera, et cetera. I just needed some data that would be fun to compress. So that's what I'm working with here. And because I have like 39 million rows in this table, and that would take a really long time, we're going to actually create a smaller version of this table with only 100,000 rows, because I can still get some pretty good results with 100,000 rows. So now we have a table called Parking Tickets Mini, with 100,000 rows in it. Just to see the size of this table, I'm going to run the following query here. And this is going to tell me that the parking tickets mini table has 100,000 rows in it. It is not compressed, right? Data compression is none. And it's a total of about 12 1/8 megabytes in size in an uncompressed state. So the first thing we're going to do is we're going to apply row compression to actually see how that affected it. So we're going to alter the table and we're going to rebuild it with data compression equals row, right? This will enable row compression on the table pretty quick, again, because we only have 100,000 rows. That's what I wanted. I don't want to sit here and have demos chugging along forever. If we run that same query again, now we'll see that we still have 100,000 rows. We have row compression enabled, and we're only using 10.9 megabytes, right? So we saved some space. We went from a little over 12 to a little under 11. So we saved, a little more than a megabyte, like 1.25 megabytes maybe of space. But this is over 100,000 rows, and this is space that really was not needed to be used in the first place. So when you consider you're pulling extra space out of thin air, albeit not much, you can see the advantage here. So now to actually get into the internals of this a little bit, we're going to list out the pages that make up the table, right? So I'm going to do a query here and select from sysdm-db database page allocations, plug in the database and the table and the index and the partition, and we're going to find the first page in the table, and it's going to return 2 for me for some reason. I still haven't figured out exactly why, but I know what the page number I care about is. It is 18281. So in a separate window now, I'm just going to open up a new query here. We're going to copy this into another window. I'm now typing in a demo. You're not supposed to do that. I'm going to copy my page number in here that we want to see, 18281. And we're going to run this query. So we're going to set dbcc trace on for trace flag 3604, which will return additional information to the session. And then we're going to run dbcc page. Let me actually view the contents of the page I specified here, page 18281. And I need to connect to the server to do that. So here we go. And what this is showing me here, this is literally the contents of the page that have been broken up for easy consumption. So every page has a header with some information about the page ID and what's stored on this page and what objects it's related to and what the next page and the previous page for, a bunch of stuff. We have some allocation information, and then hopefully this is big enough, you can see down here, we get down to the actual records on the page. Okay, so first thing we'll see here is, and hang on one second. You know what I forgot to do? I always forget to do something. Give me 2 seconds. I forgot to enable Zoom It because I'm a moron. And Zoom It would allow me to actually go in and zoom in and highlight on the screen. So I'm going to say that's worth the 10 seconds it'll take me to turn this on. Sorry about that. Here we go, zoom at 64, enable. All right, so now I can do that, right? And zoom in and actually point stuff out for you. So we're seeing here, this is a compressed primary record. We see this CD array, column descriptor array, right? So this is describing the columns in this particular row for a specific row. So, and here we actually have the contents of the row, and I'll zoom in again and show you. This is actually the bytes on disk for that row. You can see over on the right there, you can actually read some of them for the text data. You can figure out what they are, even though they're kind of smushed together, right? We have an address, 3523 West Montrose. We have a truck. We have the violation, probably, trailer, semi-trailer, prohibited, etc. And then we have all the numeric data up at the top. But what we have here is this now breaks down each column in this row by data type and by what's going on. So let me show you this here. Slot 0, column 1, length 8, length physical 3. So what that's saying is this was a column that was a big int, right, of 8 bytes long, but the number we're storing in it, which is the ticket number, which is this, only needs 3 bytes to be stored. So this is you're saving 5 bytes on this particular value because row compression is enabled. If we were to go down to another one here, right, we have the state, right, Illinois, they're all two-letter state abbreviations. Length 2, the columns of char 2, length physical is 2. There's no savings here. There's no savings here with the truck either, right, because it's 3 and 3. Over here we have length 8, length physical 7. So it's saving you space where it can, but not where it can't. So for every single column in this table, you will see a, where does the column begin? It officially begins here, where it says slot 1 there, right here. That's the beginning of a new column. We have another record, another column descriptor array, which describes the data in this particular row for the columns. And it may be different here, right? But that is the actual what's going on with row compression seen from a bits on disk perspective. Are there any questions about row compression before we move on to the next session on
This is pretty funky, Bob.
page compression? Pretty funky? I'm assuming that means good, right?
Yes, yes.
All right, awesome, cool. All right, so with that in mind, that's a very brief primer on row compression, how you can see what it's doing from a conceptual and a practical standpoint. So we're going to move back here, and we're going to go on to page compression and turn it up a notch, right? Okay, so page compression does 3 things when you enable page compression. The first thing it does is apply row compression. So everything we just talked about, that happens automatically when you enable page compression. Next thing it will do what's called column prefix compression, and then it will do column dictionary compression. So basically it is going to add, on top of that column descriptor array, it's going to add what's called a compression information structure to the page, and it is going to determine how can I deduplicate the data on this page. That's why it's called page compression. It applies to an entire page, not row compression, which literally just applies to an individual row. Page compression may not occur on every page, even if you enable it for an entire table. SQL Server is smart enough to determine, hey, can I actually save some space with page compression? If so, it will enable it for that page. If not, it won't. So it'll only be utilized on pages where space can be saved, and it only applies to leaf level pages in a table structure. So in our very, very small graph of a table structure here, remember we have the leaf level pages would be the pages at the bottom, right? So we can have intermediate level pages, which essentially will just contain pointers to the row below it. If you're doing a full table scan, you're literally just scanning all the leaves because that's where all the data is, and there's linked lists linking between these pages. But if you're doing quick index accessing, you'll usually come in from the top and figure out where you need to go. But this applies only to leaf level pages. So first thing page compression does is, again, come up with a prefix. And the prefix is in terms of byte values. So no matter what data type we're talking, we're forgetting data types at this point. Everything is just bytes on disk to page compression. What it's going to do is it's going to look for the largest, most common prefix for a particular column and store it in what's called an anchor record. Okay, and then row values are all stored in terms of this anchor value. So for example, if I have some byte values in my table with only 2 rows in a column, and they are this, as shown on screen here, the largest, most common prefix in this case is going to be 0, 1, 2, 3, 6, right? So even if we have repetition that happens later on, right? You'll notice both of these values differ by 1 value here. 1 is 8, 1 is 7, and then they're the same beyond that. That doesn't matter. We're only looking for the largest, most common prefix for each value in a column. So we're going to make this a little more graphical again and hopefully explain it better. So I have a table here. My table has 3 columns and 3 rows in it, and I'm looking at a data page. So my data page has, of course, the page header, has the compression information structure, which is created when we enable page compression. There's nothing in the compression information structure yet. That's what we're going to be figuring out. And then we have our 3 rows and our 3 columns. So the first thing we need to do is create this anchor row, which again will contain the largest, most common prefix for these columns. So in the first column, the largest, most common prefix, the value, I should say, with the largest, most common prefix is AABBC. And the way I come up with this is we have AABB, we have CAB, which shares nothing with anything, and we have AABBC, right? So AABB is clearly my largest, most common prefix in this column, and we're going to store the value with the largest that shares that. So AABBC. We have AACCBF for the second column. Again, you'll notice here we start with AACCBF, we have AACC, which shares the first 4, and the third value is AACD, right? So it shares 3 with everything, but 4 is larger than 3, so we're looking for the longest value with the largest, most common prefix to be our anchor value of that column. And for the third, it's BCDFA because it starts with BC, which it shares with one other value, and CAB does not match at all. Okay, so these are our anchor values for this particular page for those columns. Hopefully this is making sense so far. The next thing we're going to do is we're going to take all of the row values for each column and express them in terms of this anchor column. Okay, so what that means is for this first column and this first row here, this AABB value, it shares the first 4 values with the anchor value, right? So instead of storing AABB, we can just store the number 4, right? And behind the scenes, the database engine will know that, hey, that means I match the first 4 values of the anchor. And that's all we're storing. And think about it, storing the number 4 is a lot smaller than storing 4 bytes for the other values. So we just save some space here. Keep that in mind. Next, we have CAB, which has no match at all, right? It has nothing at all in common with the anchor column. So what we have to store here is literally 0 CAB. Pardon me as I cough again. So basically this means match 0 values from the anchor column and then append CAB after that. And for the third,
Bob, you're on mute.
I'm still on mute. I'm sorry. I muted myself so I could cough and you wouldn't have to listen to this. So what we did here was we the third value here, right? 0 CAB. So we're matching 0 values from the anchor column, right? Because none of them match. We're appending CAB after that. The third value is null, which means match the anchor column exactly. So that's how we're taking this first column here and expressing it in terms of the anchor column. There we go. I'll make sure I'm not muted this time. Okay, so for the second column, we're going to do the same thing. AACCBF is the anchor value.
You're muted again, Bob.
Okay, I don't know what's muting me. I'm not hitting mute there, so I'm really not sure. Well, how much of that did you miss?
Last couple of sentences.
Okay, so
Yeah.
so AACCBF, so null means point to the anchor row. 4, of course, means point to the first 4 again, because that was AACC. The third value here, AACDE, is matching the first 3 of the header row, and then appending DE after it. So it would actually store 3 DE saying, hey, match these first 3 from the anchor, and then the 2 after that, or append DE after that. Same for the third row. Yes,
question on the first row then.
Uh-huh.
Wouldn't the first one, the where there's a 4, shouldn't that be 4 and then C?
No, because that was AABB. Here, you mean?
Yeah. Oh, that's right. Okay. Never
It started off as AABB, so we
right.
only need to match the first 4.
Yeah, thanks.
So this is BCDFA. We're going to match the first 2 and then put a B after it. And then CAB doesn't match anything at all, right? So that's going to be 0 CAB. So what we have here is we have now expressed all of the values in this page in terms of the anchor value for their column. Okay, but that's only part of page compression. That's the prefix compression part of it. So we compressed based on these prefixes, and really we deduplicated in a lot of ways. We deduplicated by common prefix. Next, we're going to do another step, and we're going to do dictionary level compression on this. So now we're going to deduplicate this across columns, not just within a column, but any other column that's also, pardon me, on this page. We will create an array in that compression information structure and store dictionary entries based on things that are shared across columns, right? And it only gets written here if it repeats in 2 or more columns, but here's what that will look like. Going back to where we left off, we're now going to create this dictionary here, and we're going to say, hey, look at that. I'm storing the number 4 in 2 different columns, right? So my dictionary value is going to become 4, and the values here are just going to become index 0, right? Saying, hey, look at the first entry in the dictionary to get the value that comes in here, and then you can translate via the prefix and figure out what the value should be. Similarly, we can do the same thing with 0 CAB here in the dictionary and change that to index 1. So now we have this page that we have deduplicated via the anchor values, via prefix, and then also across columns with the dictionary values. And this is what page compression is actually doing. So we can do, I'll do a demo here and show you that as well, just to show you what that looks like. But are there any conceptual questions before we get to the demo? No? Okay, cool. All right, so we're going to go head back here to Azure Data Studio now, and we're going to take the same parking tickets mini table with 100,000 rows we were working with before, but we're gonna page compression now instead. So we're going to rebuild it with page compression.
Hey, Bob,
Yes?
One question. With the physical storage, what if nulls are allowed in the field? How does that affect?
Okay, so I might have been muted when I said this. The null you see here is not like SQL Server null. It is a different type of null. So basically it says, it's essentially pointer to anchor row. But in all the documentation I was able to find, they define it as null. But yes, if you have a null value in your column that you're compressing, remember going back to row compression, that takes a 0 space as well. So there is a different pointer that points and says, hey, this is actually a null value.
Okay.
So yeah, we're overloading the term null here, and I apologize if that's causing confusion, but that's an excellent question. Okay, so we're going to rebuild our table with page compression now, which again is nice and quick because there's only 100,000 rows here. And if we run our query we did before to see what the size looks like, we'll see that, hey, we now have page level compression on our 100,000 row table, and we're down to just a little bit over 5 megabytes. Remember, we started at like 12.1 and we went down to like 10.9. So now we pretty much cut that in half, or actually a little more than in half, even to 5.195 megabytes for our table size. So we got some good compression out of page compression here. We're going to run the same query I ran before to find the first row of the page, because remember, we rebuilt it, so it's changed. And we're going to look at page number 27816. So I'm going to go back to my other window here and type in 27816, and we're going to see what happens when I run this. Okay, so looking at the internals of a page compressed page now. So we have our page header, which again has all kinds of metadata about the page itself. We now get into, here we go, and I'm going to zoom in here. We have compression info, right? The compression information section of the page, and we have raw bytes about that. And these are going to be some things that might be somewhat readable, as you can see here, but a lot of higher level byte values that are not, because we're storing things like index locations and byte prefixes and whatnot. So that's in here. Then if we go further down, we will actually get to a regular row, right, where it says primary record. We again have this, and I'll zoom in here for you. We again have this CD array, column descriptor array, describing the bytes of the column. And then we'll actually get to the values in the compression for the values here. Or actually here we have, I forgot about this, we have anchor record information here. You'll notice we do actually have, it is null anchor record, so it is an anchor record entry, but it is in column 2. So this is the anchor row we talked about. We have the memory dump, and then hang on, where do we get to? Oh, now we have the dictionary entries, so it's breaking this all down for us. So you can see the dictionary entries, just trying to get you to a regular row so you can see what we have here. So here we have a actual record, actual data record, column descriptor array. Again, you'll notice in this column descriptor array, we have a lot of nulls, right? And that isn't necessarily because it's null. That could mean because it's a pointer to something in the compression information now. So when we get here, oh, look at this. Okay, so either, and I can't tell you which, but let's look at this here. So we have, length 8, length physical 1, which is awesome. The plate number is actually, in this case, null. Looks like, because it's the first row, and I think the first row had a bunch of null data in it, so that makes sense. You'll notice again, length 0, length physical 0, so the null values literally take up no space because of the way it's handled in the structure. Let's go down to the next row and see if it is. Okay, so here we go. We have some here that are not null, but it might make a little more sense. This is the next row. Okay, so we have, again, big savings in the ticket number, some savings in the license plate number, the state, right, Illinois. Well, these are Chicago license plate tickets, so most of our state is probably going to be Illinois, which is why the physical length is 0 here, because that's somewhere in it's either the anchor value or it's in the compression information structure, and it's a pointer to that array. So that's taking up 0 space. The type of license is a passenger car, again, probably the most common, so that's going to take up 0 space as well. Now here's one where compression doesn't help us, right? Length 4, length physical 5 for a Volkswagen. So to me, what that says, and I could dig deeper into this, but what probably happened is our anchor value is not Volkswagen or not anything close to it. So remember from the example, we're storing 0 and then the value. So that's probably why our physical length is actually longer than the length that it is, because it has to have that 0 pointer that says, hey, ignore the anchor row and then go on from there. So you can see that compression can actually take up more space in suboptimal cases here. Any other questions about just looking at these internals of row compression, or I'm sorry, of page compression? So very quickly here, just to finish this out, you can see the compression status in the sys.partitions table, because compression actually happens at a partition level, not a table level. So you'll see most of these partitions are none, except we'll have one that's page and one that's column store, and we'll get to that in a little bit. If you wanted to filter out all the system objects, you would see the non-system ones. So we have a none index, we have the page index, we have a column store index that again we'll talk about. If you're curious if your database is using any Enterprise Edition features, because compression used to be an Enterprise Edition feature and then it stopped being that in SQL Server 2016 Service Pack 1, I believe. You could look at persisted SKU features and that will actually tell you what are you using. Compression will still show there even though it's not required for Enterprise Edition. There's also a SP estimate data compression savings stored procedure that will take a sample of the table. It'll read like every 20th page, I believe. It's like a 5% sample. Try to compress that and then extrapolate how much space compressing a table may or may not save you. So you can estimate that way without actually doing it, even though, in my opinion, the best way to see is to really make a copy of the table somewhere and try compressing it and see what happens. So that's this.
We have a few questions, but there's only, like 9 minutes left. You want to just complete and then answer at the end?
I was just say I can go a little over the hour. I don't know what the timing of the group is. I can.
Sure. Why don't you work on the presentation and we'll ask the questions at the end?
Sure. That's fine. That works. Okay. So that's page compression, and actually we're almost done here. We have a little bit on column store compression, but not a ton. So the compression information structure that I showed you that had the dictionary and the anchor row, that can be rebuilt in a page on an all or nothing basis. So when you update rows that are page compressed, that might not actually trigger a rebuild, but if you update enough, that could trigger a rebuild. And the algorithm for that is if there's more than 25 modifications to a page or more than 25% of the rows on a page are modified, then it will try to rebuild it, but it will only actually go through with the rebuild if it creates enough space for 5 or 25% more rows. So there's some logic here to how rebuilds happen at the page compression level when the data changes. I have these slides, which are just the syntax for how to enable or disable compression. I'll skip through these to save a little bit more time, but the syntax is pretty straightforward. You can also rebuild individual partitions, as I mentioned, because compression really happens at the partition level. So you can actually specify rebuild specific partitions in your alter index statement. Someone asked earlier about backups and TDE. So how does compression play with TDE? Well, as I mentioned, compression takes place in these access methods. TDE only encrypts data that's on disk. So you can actually use the same two together. And the reason being because the data is compressed before it is encrypted. If the data was encrypted before it was compressed, then the compression wouldn't be able to do much. But you can always compress something and then encrypt what's compressed. That works just fine. So they play nicely together. In fact, I work on plenty of databases on a daily basis that have both data compression and TDE enabled. Backup compression is different. This was another question we got earlier. Backup compression is a proprietary algorithm to compress the backup stream. And the backup stream is literally a stream of the pages that are on disk. So it will save you space with your backups, and it will work if you are using data compression. Your net effect may be lower because the data is already somewhat compressed before backup compression tries to compress it, but you will save more space. What can't be compressed? System tables or anything not on a data or an index page. So if you have binary or large object types like those listed here, text, end text, var binary, image, SQL variant, the things that hopefully no one actually uses, those can't be compressed. And varchar max cannot be compressed either, as mentioned earlier. How much space do you save? It depends. I told you about this compression savings store procedure that will tell you. It is available in Standard Edition after SQL 2016 Service Pack 1, so hopefully you're using that or later. When should you use it? up to your organization, up to the data you have. I can't tell you when it's better or not to use it, but I can tell you that row compression can probably be used almost all the time, and page compression more or less the same. I work in environments where they just enable compression by default. I don't think that's a bad idea. What if my storage array does compression? This is a good question. Test it, right? Your storage array will probably, and by probably I mean undoubtedly, compress better than SQL Server row or page compression because your storage array will probably have CPUs dedicated to this work, right? SQL Server does not. SQL Server had to come up with something that was relatively quick and pretty good. Storage arrays can do way better than that. But the con of the storage array is your data will not be compressed in memory like it would be if you use SQL Server compression. So something to keep in mind there. With that in mind, I forgot about those slides. Let's delve into column store compression quickly here. We won't end. We'll go a little past the hour, but shouldn't be too terrible. Column store compression was first introduced in SQL Server 2012. And back then it was read-only. It was non-clustered column store indexes only. It was Enterprise Edition only. You kind of had to come up with use cases where maybe it would be beneficial for you. But it's gotten way better over time, right? In 2014, they made those column store indexes, or they made updatable clustered column store indexes. So now you could have non-clustered or clustered that were updatable. In 2016, they had updatable non-clustered column store indexes. Now you could also create secondary B-tree indexes, and it was available in standard edition. So that was kind of cool. In 2017, they added adaptive query processing and computed columns, which you couldn't have in a column store index before. And then in 2019, they added online building and rebuilding of clustered column store indexes as well. So it went from being something that was very much like, okay, I guess this is a feature. How do I actually use this? To something that's pretty darn practical at this point if you have the query workload that would benefit from a column store index. I don't know if I say this elsewhere in the presentation, but I'll say it now. Not every problem can be solved by a column store index. As a consultant, I can tell you I've walked into lots of shops where they've had performance issues, and I've heard something along the lines of, well, we created a column store index on it, but that didn't help. Well, guess what? A column store index isn't going to solve all your problems. It isn't even going to solve most of your problems. You have to have a very specific type of operation to benefit from a column store index, and then it's awesome. But the rest of the time, you're probably not doing yourself any favors. So how do column stores work? We're going to start with a relational table here, or a row store index, which is everything that's not a column store in SQL Server. We'll call a row store for purposes of simplicity here. And we're going to divide that row store index up. And we're going to divide it up into row groups, or groups of rows. And then we're going to compress each row group on a per column basis. So we went from the one big box to all these little boxes, which is literally each column compressed on a row group basis here. So we have row groups, we have columns. Each blue box is called a segment. So that's the terms we're using here. Additionally, we have in a column store index, we have what's called the delta store, or a delta row group. And these are row store indexes that contain the changes that have been made since the column store was last rebuilt, right? You can make changes, but the change is not going to actually go into the column store. It's going to go into this delta store. And there may or may not, there's at least one delta row group. There may be more than one. This image is kind of misleading in the way it's done. But this is a regular clustered index. Okay, and then together they are known as the delta store. We also have a process along the side called the tuple mover, which will help determine when a column store segment should be rebuilt, and we'll take the changes from the delta store and apply them and recompress there. But there's a lot of moving parts there, as you can see. We're just going to talk about the compression types that are available in a column store index because there's a bunch. And the engine decides what is being used. You get no control over this. It's actually kind of a black box. So there's some materials available on it. This may not even be a complete list of the compression types available for column store. But the first is, and these can be kind of simple, value-based encoding or value scale encoding. So we're going to create a mathematical relationship between a value and the stored value. So if we have some values here, All right, we got 5 different values, 1105, 1109, blah, 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 blah. If we do some very quick analysis of that, we can see that, hey, the min is 1105, the max is 1122. We would need 11 bits to store all those values, but if we translate them and we subtract the minimum, right? So we subtract 1105 from all of those, now we go from 0 to 17, and we only need 5 bits to get this value, and our base that we would just add to is 1105, right? So you just saved a ton of space just because your data is relatively the same. This, of course, only works for integer types, and this does not have to be subtraction. This can be a more complex mathematical operation, but the idea here is if we can apply some simple operation and reduce the number of values we're storing, or reduce the size of the values we're storing, we just saved a ton of space, right? So that's how value scale works. Next is bit array. This would store a bit column for each distinct value found. So maybe if you have a data type or storing some data that doesn't have a whole lot of different values in it, like maybe you're storing blood groups here, right? There's only so many blood groups, like I have on the screen at the moment. We can translate this into a column for each value found, right? So we have A, B, O, and A, B here, and only one of them will be true for each. But we just took the trick of, instead of storing, a different string or set of characters, well, now we're storing a total of 4 bits for each column, right? You can tell very quickly if a value is present without scanning just by looking at these bits. You can join, you can use these as a bit mask, or rather the engine can, because the engine's doing this behind the scenes and you don't even know about it. But that's how bit array encoding works. There's dictionary encoding. So we're building a dictionary of these values and we're replacing data with them. So let's say we have vehicle information here. We have some different car makes here, right? We can dictionary encode them and map, Chevy to 0, Ford to 1, Audi to 2, Tesla to 3. And now instead of storing character data, again, we're just storing simple numbers, right? In fact, you can map any data type to be simple numeric values like this and have very small values that take up less space. So it's data type independent and it simplifies things in the engine, and you only need so many bits for an ID, so you get great savings there as well. I mentioned at the beginning of this presentation Hofmann Coding, which is a optimal prefix algorithm, so figures out more common values and represents them by using fewer bits. So sticking with this dictionary of auto makes here, maybe we would encode Chevy as an ID of 0 because there's only 1 bit required, and I believe Chevy is still the #1 selling brand in the US overall of all vehicles. So it's more common than, say, Bugatti, which, probably doesn't sell nearly as many. So we can use a larger value to encode for Bugatti, which would require 7 bits in this case if it were 95. But that's okay because there aren't as many of them, so our data would be still smaller overall. This is based on the frequency of occurrence that would be used. We also have run length encoding, which would avoid repetition by grouping the same values together. It tries to avoid repeated values altogether. This is based on ordering, right? So it depends on the repetition pattern of the column. So let's say we're storing colors in a column, and maybe we have 105 columns that are red and followed by 92 that are blue, right? If it's set up this way, and if our cards, and the stars align and whatnot, we could actually run length encode these into just this, right? Red 105, blue 92. And then the engine would know behind the scenes that, hey, if I'm selecting from the first 105 rows, the value is red, next 92, it's blue. But if your data is sorted differently, then that might not be nearly as efficient, right? If we go red, blue, 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 etc., now our run length encoding becomes a bit more complicated, and the space savings are less so. You can also combine run length encoding with a dictionary. So you can take the values we did here and then further do them with the dictionary. So red is 0 and blue is 1, and now you save space there as well. So there are all these different types of data encoding that can be used in a column store index. And I have here very quickly, again, I know times of a premium, I'm going to drag over, I have column store compression examples. Now I have already put this table into a column store to save us some time, and I'm working with the full table now, so I have like 36 million rows in it. But if we were to select from parkingtickets.sys column store row groups and select the table, and I gotta connect to my server real quick here, you will see, oops, sorry, didn't mean to do that. What we have here is a list of all the row groups for this table. So we have about 36 million rows, and you'll notice there's about 36, in fact, exactly 36 row groups. This is because a row group in a column store index is 1,048,576 rows. That is the goal, to have one row per byte in a megabyte, right? So 10 to the 30th power, whatever. So we'll see there are some here down at the bottom that are slightly smaller, like the last two, but otherwise they are all that size. Okay, but what happens if we add a row to the table? Let's see. So I'm actually now just going to insert a row into this column store table, right? So boom, added a row. Now let's requery that list of row groups really quick here. What we're going to see is, if we go down to the bottom, we now have a row at the bottom, which instead of being compressed, it is open and it contains one row, right? That is your delta store. That is a row store index. In fact, it has a hopped ID, right? Hash or a binary tree ID, hash or B tree, sorry. Just like any other row store index in SQL Server, because guess what? It is one. So that's what it's actually showing here is we have a delta store hopped ID. In the delta store, it is literally containing that one row that we added. And now if you were to select from the table at a whole, the engine behind the scenes is going to combine the values in the column store with that delta store. You can look at the segments in the index if we wanted to just see. So this is, remember the segments is there's a segment for every column in every row store group. So you'll see there's lots more of these because there's 36 times the 8 or 9 columns that are in here is how you arrive at this number. If we were to pick one, so we're going to take the hopped ID from here and I'm going to plug it in here just to try to see if we can find real quick some of the dictionaries that are associated with this column store index. So there's a view for that, sys column store dictionaries. You'll see we have a partition ID. These are the column IDs. These are the dictionaries. What type of dictionary they are, you can get the name from those. Sorry, I'm going really fast here at the end. And if we were to run this, we will see, okay, these are the actual indexes that we put in this dictionary. Dictionary types are this. So it will tell you how they're actually being stored based on the compression types that I worked through previously in the presentation. So if I were to plug in that group to this ID, we will get encoding types for this one. So string store by value, value based with a base ID, like I mentioned. So it's using that base to figure out the values. So it'll actually break this all down and show you exactly what the column store is doing to achieve this particular result. So I have one more thing here I'll show you, which I'll try very quickly. We'll see if this works or not. I'm going to paste this into a separate window. Give me a new query window here. Throw my hopped ID in there. Oops, nope. Sorry. That value. Connect it up. Okay, so we're looking at a particular DBCC CS index, right? DBCC column store index for a particular hopped ID for a particular column and a segment. And when we look in here, we'll see run length encoding header, right? So it's doing actually run length encoding arrays, the actual values here. So this is showing, hey, for index 0, remember run length encoding where I had the colors and I said, you know, the first 100 were blue and the second 92 were red or whatever. It's actually doing those here for this particular index. So you can see the first 825,000 values have value number 20, which is a dictionary encoding for something. The next 9744. So they'd actually pick this index type or this compression type based on the column that we're doing here, which is the car license type. So this is undoubtedly the passenger license type, and it applied it that way. So that is the end of my demos here. I think I have like 2 or 3 more slides and we should be good to go. Column store compression syntax. Again, this is easy to look up if you want to apply column store compression. There's also another type called column store archive compression, which will compress even more for less frequently accessed data. It will give you a higher level it basically adds another layer of compression on top of the normal column store compression. When should column store be used? Queries that scan large amounts of data, especially on large tables or data sets that are very repetitive, data warehousing workloads, etc. Don't just think you can use it anywhere and get good results, because with normal OLTP operations, you may not. When should it be avoided? Small tables, tables that are very unique data, queries that return all rows in the table. It won't be any faster if you're returning all rows from a column store index than from a row store index, or things that are frequently updated, because then again, it'll just be going into a row store anyway. Okay, so good resources if you're looking for more information where you can learn more about this stuff. Jonathan Cahias has a great blog on how to use extended events to track compression operations. Nico Negebauer has an entire blog series on column store indexes, like over 100 posts on column store indexes, their uses, and the internals. And you can find everything else at this link at the bottom, pusateri.com/r/compression. It will take you to the slide deck, the demos, the demo database, and all the materials I just linked to. So with that in mind, I have a hard stop in 19 minutes, but if we have any other questions before then, I'll be happy to answer them.
Yes, there are some questions in the chat. Is there a viable use case for choosing row compression over page compression?
Is there a viable use case? I would say in most cases, if you can benefit from row, you'll also benefit from page. I remember back years ago when I worked on systems that were rather resource constrained, we were kind of selective on what tables we applied page compression to. There was generally always some really good savings that could be had from row compression, but the types of data we were using didn't always deduplicate well with page compression, in which case we'd leave them on row compression. So I think that's why they give you the option of either or. But for most cases, especially for regular OLTP data, I would argue that if you can benefit from row compression, you can also benefit from page compression.
Okay, are there any situations where the extra CPU needed becomes a problem, like continuously updating the same row as an example?
I'm going to say if you're using any halfway remotely modern hardware, no. The CPU hit for data compression was, I believe, less than 5%, and that was in 2008 on 2008 hardware. I would really hope anything you're using today is better than that. So while there absolutely will be some level of CPU hit, because we're doing more work that doesn't come free, it should be minimal to barely noticeable. If you're noticing that the compression is placing you over a tipping point on performance, I would start to question how are things configured the rest of the way. Like it may be indicative of a larger problem in your environment or on that system.
Any noticeable changes in the context of the database transaction log, usage/size, to be aware of when turning it on for very large indexes?
I mean, when you do the actual rebuild to enable compression, it's an index rebuild, right? So that's going to write out a whole bunch of transaction log regardless. But beyond that, I would say no.
Let's see, if you compress your table, will compressing the indexes of that table yield any improvements in query performance?
That's going to depend on an individual basis. I mean,
on the query,
likely yes. I would say generally you should see performance improvements, because again, you'll be doing less I/O, you'll be reading more from memory, etc. But these are the things you need to go test in your environment on your hardware with your data.
What's the best way to compress XML or nvarchar, compress/decompress?
So as I mentioned, XML and nvarchar are both encoded as Unicode. So there is Unicode compression that can take place. It's not guaranteed to. So this is, again, something you need to experiment with. But if you have large blocks of XML, this is where things may be better if you actually use SQL Server's native XML features. I try to avoid XML in my databases like the plague. I'm guessing many of you do as well, though I know sometimes you have vendor software or whatnot where it's unavoidable, but that'd be something you need to experiment with.
How much, I guess, how much can decompression cost us from a page compression?
There's no way for me to know how much it's going to cost you. I mean, that's again, it's going to be a cost. It's going to be minimal. Try it out in your environment and see.
Yeah,
the best advice I can give you.
I guess that's the same one for how to know if compression is causing any issues on a SQL server.
The only issue it could possibly cause would be related to performance in my mind, right? I trying to think of problem. I've never seen a problem caused by turning on compression, other than, you know, watch your performance, see how your environment reacts. So
let's see. Brent had a problem with using compression and replication, even though the article was set to honor compression. He hasn't gotten back to look at it more to see if it was something in general. Have you seen any issues with compression and replication?
And replication? No, but I also probably haven't used replication in a way that Brent has. So I can't speak for that. I can't remember the last time I actually used, and I'm assuming they mean like transactional replication or something. Mm-hmm. But because that's an overloaded term in general, but no.
I have availability groups and I use compression. You know, the compression set, it's a vendor package and they have the compression set, and I haven't had any issues with availability group replication.
Nice. Okay.
Oh, he tried doing the schema manually and didn't make any difference. We used a big mix of merge and transactional replication. I think the issue was with the merge. Yeah.
Merge replication, yeah. I have never played with, other than I've looked at it and I've went, wow, that looks horrible. I hope I never have to do it. And I guess I've gotten lucky because I haven't. So.
And I'll work with Paresh on the tiny URL for where the slides are going to be. But you can see here, Bob also has a link where he's going to post his information.
Yep, it's already up there actually. So, and actually this URL will just forward you to my GitHub page for this presentation. So again, has all the materials right there.
Well, I'd like to thank you for a great presentation. I love seeing the internals of you know, your demo with what it actually was doing. I'd never seen that before.
Oh, and cool.
Yeah, seriously, this is awesome, man.
Thank you very much. I'm glad everyone enjoyed it.
So thank you very much. Thank you, everyone, for going over with us on this. We really appreciate your time, Bob. We appreciate your extended time. And I think it was just an awesome presentation. So thanks again. And hopefully we'll see everybody back next month for our presentation.
Sounds good. Awesome. Thank you so much for having me.
Okay, guys. Bye.
Bye.
Thank you.